There's a Boeing test from March 2010 where engineers bent the wings of a 787 upward by about 25 feet before they finally gave out. 25 feet. That's roughly the height of a two-story house, flexing on a structure designed to carry 300 tons through the sky. And here's the part that messes with your head. They had to push it that far on purpose, in a lab, with hydraulic jacks pulling against the wingtips. Real turbulence in the real world has never come anywhere close. So how is it actually possible? How does an aircraft weighing as much as 50 elephants get tossed around by invisible walls of air, drop suddenly, hit pockets of chaos that send drinks across the cabin and unbuckled passengers into the ceiling, and just keep flying like nothing happened? That's the question nobody really sits down and explains properly. Not the airline, not the safety video, not even most pilots when passengers ask after a rough leg. And the answer is way stranger than just saying planes are strong. The answer involves a piece of physics so weird that it remains one of the most famous unsolved problems in classical science. We'll get there. But first, let's start with the most obvious clue. The one most people get wrong from the very first sentence. Every commercial airliner you've ever boarded has been built to handle 1.5 times the worst load it should ever encounter in service. That's not a guideline. That's the law. Federal Aviation Regulation Part 25, Paragraph 305, written in dry legal language that basically says, prove this thing won't fall apart, even when you push it past anything we expect it to actually face. And if it can't survive that test, it doesn't fly. Period. So when Boeing did that 787 wing bend test, they weren't trying to break the plane just to see what would happen. They were proving on video that the wings could bend to ultimate load, about 150% of the maximum stress predicted across the entire fleet's lifetime of normal operations, without failing. The wings did eventually fail, somewhere past that mark, but the certification only required them to survive up to the line. Going further was just confidence. Now think about what that means in real flight. The strongest turbulence ever measured on a normal commercial route doesn't come close to those certification loads. The maximum positive load factor for a transport category aircraft under FAA rules is 2.5 Gs at the limit, with ultimate load at 3.75 Gs. Severe turbulence, the kind that ends up in news headlines, typically produces accelerations well below those structural limits. The actual breaking point is higher still. In other words, the worst air you've ever flown through is a polite tap on a structure built to take a sledgehammer. And it's worth pausing for a second on what that test actually involves, because most people picture certification as a stack of paperwork, and it's not. Before any new commercial airliner is allowed to carry a paying passenger, regulators require physical destruction tests on at least one full-scale airframe. They build a complete airplane, mount it inside a steel jig the size of a hangar, hook hydraulic actuators to the wings and the fuselage, and then they bend it. They twist it. They simulate years of flights, compressed into weeks of cyclic loading, watching for cracks, monitoring strain gauges glued to thousands of points across the structure. The airplane that flies you to vacation was approved because a sister airframe was deliberately tortured to failure on a factory floor on camera, with engineers writing down exactly when and where it gave up. That's clue number one. Now here's the second thing nobody tells you, and this is where things get genuinely strange. Air pockets don't exist. Not the way you've been picturing them. There's no empty hole in the sky, no vacuum chamber that the plane falls into. That phrase, "we hit an air pocket," is one of the most enduring misnomers in aviation, repeated for over a century, and it's wrong. What's actually happening is much more fascinating and much more important to understand if you want to know why your plane keeps flying through it. Air, especially in the upper atmosphere, isn't a smooth fluid moving in one neat direction. It's a chaotic mess of currents, warm air rising off oceans and continents, cold air sinking, jet streams shearing past slower surrounding air at hundreds of miles an hour, mountain ranges flinging air upward in invisible standing waves that travel for hundreds of miles downwind. When your aircraft flies into a region where the airflow suddenly shifts direction or speed, the wings, which generate lift based on the relative motion of air, momentarily produce more or less lift than they did a second ago. The plane responds. It pitches, it rolls, it climbs, it drops. But it does not fall. There's air everywhere. The wings are still flying. They're just flying through air that's behaving badly. If you've ever driven over a frost heave in winter, where 1 second the road is smooth and the next your tires drop a couple of inches into a dip, that's roughly what's happening. The car doesn't crash. It just lurches. Same physics, different medium, same outcome. Startling, uncomfortable, but mechanically routine for a vehicle designed to handle it. The dramatic feeling of dropping hundreds of feet that passengers report, almost always exaggerated. Flight data from real severe turbulence events typically shows altitude losses of tens of feet, sometimes 100 or two at the extreme end. The vestibular system in your inner ear is terrible at distinguishing a sudden lift change from a free fall. Your brain interprets the unfamiliar acceleration as plummeting because it has no other category to put it in. The numbers tell a different story. It also matters that not all turbulence is the same thing. There are essentially 4 categories that pilots and meteorologists deal with, and each one behaves differently. The first is convective turbulence, the rough air around and inside thunderstorms, where rising columns of warm, moist air punch through the atmosphere with enormous energy. This kind is visible on radar, avoidable, and basically always given a wide berth by modern flights. If your pilot deviates around a storm cell, that's why. The second is mechanical turbulence. What happens when wind hits a mountain range, a building, a rough surface, and breaks into eddies on the lee side. That's what brought down BOAC 911, and we'll get to that. The third is wake turbulence. Air disturbed by another aircraft, especially a heavy one, leaving rolling vortices behind its wingtips that can persist for minutes. Air traffic control spaces aircraft to avoid this. And the fourth is clear air turbulence, often abbreviated as CAT, which is the kind that makes the news. Invisible, detected only by aircraft already in it, usually associated with the boundaries of jet streams at high altitude, where fast-moving rivers of air shear past slower air around them and create regions of unstable flow. CAT is the one that matters most for passengers, because it's the one you can't see coming. By the way, if you're getting something out of this so far, take a second to hit like and subscribe. It genuinely helps the channel keep doing this kind of engineering deep dive, and there's a lot more aviation content coming. Now back to the real reason your plane survives all of it. For most of the 20th century, aircraft wings were built mostly out of aluminum alloy. They flexed, but only so much. The basic philosophy was straightforward. Make the wing strong enough that it doesn't bend much under normal loads. Fight the air. Resist the disturbance. The 787 changed that philosophy in a serious way. Boeing built the wings out of carbon fiber reinforced polymer, composite, and they engineered the wings to bend dramatically. Several feet during normal cruise, much more under load. It wasn't a flaw to manage. It was a feature to embrace. A flexible wing absorbs gusts the way a shock absorber absorbs a pothole. The energy that would have hit the airframe as a sudden jolt instead spreads through the wing as it bends and rebounds, smoothing the ride and protecting the underlying structure from sharp peak loads. This is why a 787 in turbulence often feels different from older aircraft. Passengers describe the ride as softer, more compliant. That's not marketing language, that's engineering. The wings are doing exactly what they were designed to do. Give a little, take a lot, never break. And here's where it gets even more interesting. Modern fly-by-wire flight control systems on aircraft like the Airbus A350, the Boeing 777, and the 787 are constantly adjusting control surfaces in real time, sometimes faster than a human pilot could react, to dampen out the worst of the load. The plane is actively flying through the turbulence, not passively enduring it. Accelerometers and air data sensors detect changes in pressure and motion, and small surfaces on the wing, ailerons, spoilers, sometimes specially dedicated load alleviation surfaces, twitch in response, redistributing load across the structure before it can build into something dangerous. You don't see any of this from your seat. You don't feel it. The plane just rides the disturbance and keeps going. From outside, you'd see subtle control surface movements, like a tightrope walker shifting balance against a gust. From inside, it's just a slightly bumpy ride and a flight attendant telling you to stay seated. And then there's the thing pilots learn from day one of training. You don't fight turbulence, you ride it. If you're flying through severe chop and you yank the controls trying to keep the plane perfectly level, you're going to do two things. First, you'll make the ride dramatically worse for everyone behind you, because every correction you make on top of the turbulence becomes its own jolt that the passengers feel. Second, and this matters more, you'll load up the airframe in directions it doesn't need to be loaded in, stacking your control inputs on top of the natural disturbance. The plane wants to weather the gust. You're getting in the way of its own physics. The standard procedure in serious turbulence is to slow down to what's called turbulence penetration speed, sometimes called maneuvering speed or VA, the speed below which the wings will stall before they can structurally fail. Stall is recoverable in a few seconds, brake is not recoverable at all. So pilots reduce thrust, hold the attitude roughly steady, and let the plane do its thing. The wings flex, the autopilot or the pilot makes only small inputs to keep the heading and altitude generally on track, and the airframe absorbs everything else. There's a famous incident from May 2024, Singapore Airlines flight SQ321, a 777-300ER flying from London to Singapore that hit severe turbulence over Myanmar at around 37,000 feet. The aircraft dropped briefly, dozens of people were injured, and tragically one passenger died during the event. It made global headlines for days. But here's what didn't get the same airtime. That plane was flown safely down to Bangkok minutes later on schedule for an emergency diversion. The structure was intact. The engines were intact. The pilots flew it down without further incident. The airframe took the worst that the sky had to give that day and asked nothing in return. Comment below if you remember hearing about that flight when it happened. I'm curious how that story landed for people who fly a lot, because the structural reality of what happened was very different from how it got reported. Okay? So now you know about the certification margins. You know air pockets aren't really pockets. You know the wings flex on purpose, fly-by-wire damps the loads in real time, and pilots ride out the disturbance instead of fighting it. That's a lot of clues already, and any one of them is enough on its own to explain why turbulence rarely takes a plane down. But there's one more layer, and this is the layer where the mystery actually deepens instead of resolving. Turbulence, the phenomenon itself, the chaotic motion of fluids, is one of the most important unsolved problems in classical physics. Richard Feynman, the Nobel laureate, said exactly that in his famous Lectures on Physics. He called turbulence the most important unsolved problem of classical physics. Not one of many. The most important. What does that actually mean? It means we can describe turbulence statistically. We can model it on supercomputers using approximate methods. We can predict roughly where it'll occur in the atmosphere, how strong it might get, what shape it tends to take in clouds and over mountains. But we cannot, even in 2026, write down a clean mathematical solution for the chaotic flow of a fluid in 3 dimensions. The Navier-Stokes equations describe it perfectly in theory. Whether smooth, well-behaved solutions to those equations always exist is one of the 7 Millennium Prize problems posted by the Clay Mathematics Institute, with $1 million reward attached for whoever solves it. As of today, nobody has. Read that again. The air outside your window, swirling around the wing as you cruise at 35,000 feet, is governed by physics that humans have not fully cracked. We've been flying for over a century. We've designed aircraft to handle this stuff. We've built entire industries around predicting it. And at the deepest mathematical level, we still don't completely understand the medium we're flying through. So when a plane survives a violent encounter with clear air turbulence at high altitude, and clear air turbulence is the worst kind because it's invisible to weather radar, invisible to the eye, just suddenly there. What's actually happening is this. A piece of engineering designed using approximations and statistical models and 100 years of accumulated experience is interacting with a chaotic phenomenon that the smartest physicists alive can't fully describe. And the engineering wins. Every time. Almost. Because there is one famous exception, and it deserves to be told honestly. In March 1966, a BOAC Boeing 707 Flight 911 broke apart in the air near Mount Fuji in Japan after flying into severe mountain wave turbulence. 124 people died. It's one of the very few cases on record of a commercial airliner being structurally destroyed by turbulence alone, with no other failure preceding it. And it happened nearly 60 years ago on an aircraft built to certification standards far less demanding than anything flying today. The story behind that flight is genuinely unsettling. The aircraft had departed Tokyo's Haneda Airport bound for Hong Kong, and the crew elected to fly a visual route past Mount Fuji to give the passengers a clear view of the mountain. Conditions on the ground looked pleasant. What the pilots couldn't see was that strong winds were blowing across the summit at high altitude, creating what's called a lee wave, a series of standing oscillations in the air on the downwind side of the mountain with embedded rotors of violently churning air at the lower edges. The 707 flew straight into one of those rotors at around 16,000 feet. Investigators later concluded the aircraft experienced gust loads severe enough to immediately separate the vertical stabilizer from the airframe, followed within seconds by the loss of the engines and the rest of the tail. There was no recovery possible. The flight crew had no warning, no time, and no path back. Mountain wave turbulence of that severity simply wasn't on the radar of operational planning at the time. That accident, along with a handful of other turbulence-related events in the 1960s and 70s, is a major reason why modern certification standards, weather forecasting, and pilot training around mountain operations and jet streams are what they are today. The aircraft that fly through similar conditions in 2026 are designed, equipped, and operated with that disaster baked into the rules. Since then, with modern aircraft, modern composite materials, modern certification rules, modern weather forecasting, satellite imagery, pilot reports shared in real time, and modern fly-by-wire load alleviation systems, effectively zero. You can count on one hand the cases where turbulence has even come close to threatening a modern airframe. The technology has gotten that good. The engineering has gotten that careful. The clues we've been walking through, the structural margins, the flexing wings, the active controls, the trained pilot response, have stacked up into a system that handles the unknowable on a daily basis in tens of thousands of flights per day all over the planet. And yet the unknowable is still there. It's still outside the window. It's still swirling around the wing in eddies the size of a fist or the size of a city, governed by equations we can write down but cannot fully solve. The plane doesn't care. The plane was designed for a problem we haven't finished defining, and it solves it anyway. Billions of passenger hours into the experiment, with a safety record that gets better almost every year. There's one thing worth saying directly before we wrap up, because it actually matters for you personally. The vast majority of turbulence-related injuries on commercial flights happen to people who weren't wearing their seatbelts when the rough air hit. The aircraft is fine. The cabin is fine. The seats are bolted to the floor with anchors rated for forces well beyond anything turbulence will produce. But a passenger standing in the aisle or sitting unbuckled in their seat becomes a projectile when the floor drops out from under them by a few feet for a fraction of a second. The plane goes down briefly. The unbuckled passenger keeps going, hits the ceiling, comes back down. That's where the broken bones come from. That's where the head injuries come from. Not from the airplane. From basic Newtonian physics applied to a body that wasn't anchored to anything. When the seatbelt sign is on, it's on for a reason. When the captain leaves it on through smooth-looking air, it's because clear air turbulence is invisible, and the only honest answer is that nobody, including the radar, knows for sure what's a few miles ahead. The single most effective thing any passenger can do to stay safe in turbulence is the simplest one. Keep the belt loosely fastened whenever you're in your seat. The aircraft will handle the rest. It was built to. So here's where I want to leave it for you. We can describe what happens to the plane. We can build airplanes that survive almost anything the atmosphere throws at them. But the air itself, the chaotic medium they're flying through, that part, we still don't fully understand. Maybe we never will. Maybe turbulence is one of those things the universe quietly kept for itself while letting us fly through it anyway. Tell me in the comments, does knowing all this make you more relaxed about turbulence on your next flight? Or less? Honest answer. I genuinely want to know which way it lands for you because I've heard it go both ways. And if this video taught you something new about the planes you board without thinking twice, hit subscribe, smash the like button, and stick around. There's a lot more like this on the way.